Welcome to Efiwe, excellence without stress.
Hi dearest Efiwes, welcome back to our channel, and today you're going to have another awesome class. And on this our journey, you are going to become the best in physics. Today our topic is electrostatics. Electrostatics. We want to study about charges, about how charges flow, stable charges or constant charges. So we're going to talk about charges today. Electric force between charges, Coulomb's law. So the French physicist Charles Coulomb investigated the nature and magnitude of this force, just the same way as Isaac Newton studied about gravitational force, gravitational field. This physicist, studied about what? Charges. So the French physicist Charles Coulomb investigated the nature and magnitude of this force. That is the force between charges. You know that Isaac Newton investigated what? The force of attraction between masses. So Coulomb investigated the force between charges, and that was where the Coulomb's law came from. So the Coulomb's law is just like the opposite of the Isaac Newton's law. Just that Isaac Newton's law of universal gravitation was focusing on masses, the force of attraction between two bodies. And why this Coulomb's law is focusing about two charges. Their formula looks almost the same thing. The law is almost the same thing, just two charges, and is the product is also the force between them is also equal to the product of the charges and inversely proportional to the square of their distance apart, just the same way we did when we're talking about gravitational force. So he said it showed that if the bodies were small compared to the distance between them, then the force between such two bodies was inversely proportional to the square of the distance r. Can you imagine? So the F is inversely proportional to the square. You know, we did that when we were talking about the gravitational force of attraction, and this is called the inverse square law. So Coulomb's investigation showed that the force was also proportional to the product of the charges. Can you see that? Just as I said, you know, then we had M1, M2. Now we're having what? Q1 and Q2. So Coulomb's law holds only for point charges, that is objects whose sizes are smaller than the distance between them. Don't forget that Coulomb's law holds only for point charges, that is objects whose sizes are smaller than the distance between them. So the electric force between two point charges Q1 and Q2 separated by a distance r is directly proportional, you know that, to the what? To the product of the charges, and inversely proportional to the square of the distance between the charges, just as we did when we were doing Newton's law of universal gravitation. So you recall that we said that anytime we are changing the proportionality sign to equals to, what are we going to do? We will introduce a constant, and for this, K is our constant. K is our constant. So in SI units, F is in Newton, Q1 and Q2, which are charges, are in coulombs, R is in meters. The constant K is usually taken as K is 1/4 pi epsilon naught. Epsilon naught is the constant known as what? Permittivity of free space. It is known as permittivity of free space. And don't forget, K is equals to 9 times 10 raised to power 9. So most times you might not need to use it as this. You might just put it your 9 times 10 raised to power 9 Newton meter square per Coulomb square. So as we can finally say that F is equals to, you know, this is our K, which was the constant we introduced, multiplied by the square of the charges divided by the what? Distance apart, the distance of the charges apart. So this equation gives the magnitude of the force that either object exerts on the other. That's the force. So electric force between charges, Coulomb's law. The direction of this force is along the line joining the two objects. You can see now. So see, these lines, now we call them lines of force because they are imaginary lines. Ideally, the current flows out of the positive charge and goes into the negative charge, just like in magnetism. You know, the magnetic force flows out of the north pole and goes into the south pole. So here you can see the direction of the charges. It goes out from the north and comes into the positive. And why are they connecting? They are connecting because they are opposite charges. If they were same charge, they are going to repel each other. Don't forget, opposite charges does what? They attract. If it was positive and positive, then this charge, when it gets here, it will run off. No, It will run off because like charges does what? They repel, but unlike charges attract. So the direction of the force is along the line joining the two objects. Yes, it's along. So if the two bodies have a charge of the same sign, the force is that of what? Repulsion. That was what I just explained. If it was positive and positive or negative and negative, then we don't expect this connection. They can never connect. So these ones are coming like this. Okay, yes, this one will go in. They are connecting with each other because they are opposite sign. But if it was a negative sign, let's go to our board and let's see how a negative this thing is going to look like. Let's look at how the negative sign will look like, just as we had the positive. You know, now we had the positive, we had positive, and we had the negative, right? And what happened? We noticed that they were from the positive it was going into the negative. From the positive, sorry, don't mind my draw. Okay, let me delete and try again. Maybe we can have a better drawing. Show and delete. We can have a better. Okay, so let me try again. So I have the positive charge, I have my negative charge, right? So I said because they are opposite, they do what? They attract. This is just an imaginary line. It's not something we can see. Lines of force, they are imaginary lines that we assume that because this is the area where the electric effect is more felt. Sorry about this, my drawing. So is always coming out of the positive, is always coming out of the positive, and is always coming into the negative, always going inside the negative. So there is an attraction. But what if it was positive and positive, or negative and negative? So once we have positive here and we have positive here. Okay, so once it's coming like this, it will go up. Once it's coming like this, it will go up. If it comes here again, it will go up. It will come again. Also, we're going to have a space here. So don't forget, it is always going out of the positive, always going out. It's never going in. The positive charge gives out. So this is how it's going to look like. Sorry about my diagram, but I'm just trying to explain to you that it's going to be the force of repulsion. They can never attract with each other because like terms, they repel, but unlike terms, unlike charges do what? They attract. I'm sorry about my diagram. I hope you understand what I'm trying to say. So they said if the two bodies have charges of the same sign, the force is that of repulsion. The force on each object is directed away from each other, so they run away. But if the two objects have opposite charges, the force is that of attraction. The force on one is directed towards the other. The force one charge exerts on the second is equal but opposite to that exerted by the second on the first. Equal but what? Opposite. This is accordance with the Newton's third law. Don't forget, Newton's law says action and reaction are equal but in opposite direction. So if this one is directed towards this side, the other one will be directed towards the opposite side, but they will be what? Equal but opposite. Action and reaction are equal but opposite. So let's take this quick example to explain the Coulomb's law. So he said find the force of repulsion. So basically we know that the charges are equal. That has told us that we don't even need any other story. These are equal charges. So they said find the force of repulsion between two protons of 1.6 times 10 raised to minus 19 coulombs each if the distance between them is 5.3 times 10 raised to minus 11 meters. So we know we've already said we're going to take our k. Oh, sorry, there's no k there, but this is okay. 1.4 pi epsilon naught is equals to 9.0 times 10 raised to 9 Newton meter square per coulomb square. So we have that. So what was the formula? Recall. Let's go to our board and do that. Let's work it. So we've already explained the Coulomb's law. The Coulomb's law said that F, right, is directly proportional to the product of the charges, which is Q1 and Q2, right, and inversely proportional to the square of the distance apart. You can call it a D. So, and I told you that when we are changing proportionality sign to equals to, we're going to introduce a constant, which in our case is K. So we have Q1 Q2 over what? Over R squared. And we're told that K is equals to 1 over 4 pi what? Epsilon naught what? R. So 1 over 4 pi epsilon naught. Then we are going to have Q1 Q2 over R squared. And the value of this is what? 9 times 10 raised to power 9, right? Newton meter square per coulomb square. So that is it. We have all of this in. So let's check what we were given in our question. We were given our charges as 1.6 times 10 raised to power minus 90, right? So we have 1.6. So we have 1.6. So we have our what? Q. Since they are the same charges, so Q1 was equals to 1.6 times 10 raised to power what? 1.6 times 10 raised to power, let me check, minus 19. Yes, 1.6 times 10 raised to power minus 19. Yes, so we have 1.6 times 10 raised to power minus 19 for Q1. Q2 also is 1.6 times 10 raised to power what? Minus what? 19. So we can actually just say F is equals to Q square, right? Over K. We can say KQ square over what? R square, because we have the same what? Q. So that's F will now be equals to 9, right? Times 10 raised to power 9 multiplied by what is our Q? Our Q is 1.6 times 10 raised to power minus 19 all squared, right? Then over our R, which is the square of the distance apart. What is our R? Our R is 5.3 times 10 raised to power minus 11. So we have it as what? We have it as 5.3 times 10 raised to power what? Minus 11. So we can solve this. Yes, we can solve this. You can actually use your indices to get this. You know, this one is going to become, if you have it like 9 times 10 raised to power 9, right? Then we have times 1.6 square, right? Then that will be 10 raised to power minus 38, yes, over 5 times 10 raised to power minus 11. So you know we can subtract this, then bring this up, and when you use your calculator, you are going to get it as, well, that is the force of repulsion between the two protons. That's the force of repulsion. You can see how much they repel, that they don't even want to be together at all. So that's the force of repulsion, no attraction. Electric field intensity, and electric potential. There is an electric force between 2 points. Yes, between 2 points. There's an electric force between point A and point B. How can one electric charge exert a force on a second charge even though they are not charged touching? How does that happen? How can one electric charge exert a force on a second charge even though they are not touching? According to Michael Faraday, an electric field extends outward from every charge and spread out through space with the charge as center. So this is it. An electric force extends outward from every charge and spread out through space with the charge as center. So any charge placed near the first charge experiences a force because of the effect of the electric field of the first charge. The electric field of the first charge interacts directly with the second charge to produce a force. So we can define electric field as a region where an electric force is experienced by a charged body. So an electric field, just like a football field, that period, that place, an electric field is a region where an electric force is experienced by a charge, but just like a gravitational field is that area where the force of gravity is duly felt. So we can define electric field as a region where an electric force is experienced by a charged body. An electric field is investigated by measuring the force on a small positive test charge. A test charge is a charge so small that the force it exerts does not significantly alter the field it is testing, doesn't affect it at all. So a test charge is just a tiny charge and it does not affect the field that it is what testing. With the aid of the test charge, you can map out the electric field. Yes, so using the lines called electric lines of force. So we can say, okay, this is the area where the electric field is duly felt, where the electric charge, the electric force is experienced or felt. Thus, an electric field is represented by electric line of force. They are imaginary. We just assume that these are the places where the force is felt. That when you come to this place, this area is the area where the electric force is felt. Electric line of force are imaginary lines drawn in such a way that the direction at any point, that is the direction of the tangent, is the same as the direction of the field at that point. Or the line of force is the path which an isolated small charge would follow if placed in the field. That's the path it will follow. So it is just an imaginary line that was an isolated small charge. You can see it would follow if placed in that field. Like we saw the positive charge, we saw the negative charge, and we saw the way they are moving, we saw the direction. The strength of an electric field. Strength, we talked about it too during the gravitational field in terms of force on a positive test charge. So the strength of an electric field is defined in terms of force on a positive test charge. So the force itself depends on the charge of the body and on the field strength or intensity. So the strength of an electric field at any point is defined as the force per unit positive charge at that point. So E is F over Q. Very simple. E is F over Q, and it is measured in Newton. You know, F is measured in Newton, Q is measured in coulomb. So Newton per coulomb. So F is measured in Newton and Q is in coulombs. So, and this is the field intensity, and this is the field intensity. Since E is a vector, the electric field is an example of a vector field. Electric field or field intensity are added by the usual vector methods. Thus, the electric intensity at a point due to several charges is the vector sum of the intensities due to individuals. So if you want to know the total intensity at a point, so you have to add the intensity of different points together. So we can see that F is equals to what? QE, and E is equals to F over Q. So electric force is equals to electric charge times electric field intensity. So look at it now. We can obtain the equation for the field intensity due to point charge Q at a distance R. Look at it now. These are two charges, and this is the distance between them. So we want to know the electric field intensity. We assume that the point charge is situated in a vacuum. So the force between point charge Q and the test charge Q, this is the test charge, is what? F is equals to 1 over 4 pi epsilon naught QQ over R square. So we have E equals to F over Q. Don't worry, we're going to go and solve this and get this. So we have that our field intensity to be equals to this. Don't forget that we have that E is equals to F over Q. Let's go to our board and explain this. So recall, let's go back. We have that our E to be equals to what? F, right? Over what? Q. And F itself is equals to what? K, right? Q over what? Over R square, right? So if F is this, so it's as if we are saying E is equals to K, right? The capital Q, the small q over R square, right? Then divided by another Q, right? So this Q, we cancel this Q. So automatically your E will be equals to K, right? Q, capital Q over what? R square. And we can also write it as E is equals to 1 over 4 pi epsilon naught, right? Then the Q will be on top. So this is the electric field intensity formula, and that's how it's related. We got it from E is equals to F over Q. So are we clear with that? Yes, we are. So that is it about that. So that is how we got this formula as E is equals to 4 pi epsilon naught R square. Did we put our R square? Oh, sorry. I forgot to put the R square. So E is equals to Q 4 pi epsilon naught R square. Yes, you know there is R square here. Sorry for that mistake. So the R square is there. So we have that. So that's how we got our field intensity at B. So easily, they said we have the question, calculate the electric field intensity in a vacuum at a distance of 10 centimeter. We have to convert that to meter from a charge of 5 times 10 raised by minus 4 coulomb. Okay, very simple, right? So we're asked to find the electric field intensity, we're given the distance, and we're given the charge. So easily we can get this from what we did. So E is equals to Q over 4 pi epsilon naught R square. This 1 over 4 pi epsilon naught is what? 9 times 10 raised by 9, right? And putting in the right parameters, we will get our answer. So simple. Our Q was given 5 times 10 raised by minus 4. This is it, right? Our K, which is this, 1 over 4 pi. So this is it here. And our epsilon naught, and that is it. So I'm sure we understand the way we solved that. Electric potential. Electric potential V at a point is defined as the work done. So potential difference is actually the work done. You know, when you say potential, we're talking about the energy a body possesses by virtue of its position. So potential at a point, electric potential at a point is defined as the work done in bringing a unit positive charge from infinity to that point against the electrical force of the field. So the electric potential at the point is work done. The work done most times is the point of moving one charge from one point to another, from moving it from one point to another, say at infinity distance to that point. So electric potential at a point is defined as the work done. Like as if I'm pushing you. Maybe you want a car is at the ground floor. There must be an energy needed to push it from the ground floor to the hill. So it is the work. You remember when we talked about work done? Work done is force times distance. So that is why it is work done. Work done, work done, without moving in a distance, without it leaving where it is. Work has not been done. So electric potential at a point is defined as the work done in bringing unit positive charge from infinity to that point against the electric force of the field. So consider 2 points A and B. So if you look at the points A and B in an electric field, if more work is done in bringing unit positive charge from infinity, bringing it from infinity to A, bringing it from infinity to A and B, we say that A is at a higher potential than B. You understand that? They say if more work is done in bringing unit positive charge from infinity to A, we are bringing the unit charge from infinity to A, than when we are bringing it from what? To A than to B, we say that A is at a higher potential. That is, we need more work. If more work is done in pushing A than it's done in pushing B, I told you that this is work done. Maybe A is at a point, then we want to push it from infinity to that point. If more work is done in pushing that charge from infinity to A, then we believe, and then when we are pushing it from infinity to B, we actually believe that A has more potential than B. It's so simple, because we are doing much more work in pushing that charge from infinity to A than we are doing when we are pushing it from infinity to what? To B. There is then a potential difference. Yes, a potential difference between A and B. There's a potential difference, because the one we needed to push it from infinity to A is different from the one we needed to push it from infinity to B. So what will be the potential difference? It will be the one from A minus the one of B. So the difference in potential is equal to the extra work done in moving the positive charge from B to A against the electric field. The extra work done. Potential difference, potential difference VAB between 2 points A and B is the work done. Don't forget that in taking unit positive charge from one point to the other in the electric field. The work done in taking it from A, look at V, from that's potential of A and B. So taking it from a point to another is the work done. Both the potential and the potential difference are scalar quantity having the dimension of work per charge. So 1 volt is joule per coulomb. That's work divided by the coulomb, which is the charge. So we have that the potential difference between 2 points is 1 volt if the work done in taking 1 coulomb of positive charge from one point to another is 1 joule. Do you understand that? We said the potential difference V is 1 volt. Just imagine now we have V is equal to W over Q. So if work done is 1 and the charge is 1, V will be equals to 1. So the potential difference between 2 points is 1 volt. This is it now. Let's assume we have V is equal to W over Q. So it will be 1 volt now. Definitely, if you have your work done, it will be what? It will be 1. If the work done in taking the positive charge from one point to another is 1 joule and the charge itself is 1, then we have our V to be what? 1. Also, it can be shown that electric field intensity is related to the electric potential difference between 2 points through this equation. So E, you know the former one, we said E was equals to F over Q. Also, electric field potential and this potential difference, they have a relationship, and that is E is equals to V over D. That's the relationship between them. And also we know that V is equals to ED. Can we actually get another formula for this? Yes, we can. Because if we add that our V is equals to ED, recall what we got as our E, right? Recall what we got as our E, then we put it here. We can change it to D. So let's go to our board. Okay, you know we said V now. We are saying V is equals to, I'm coming. So new clip and coulomb. Okay, sorry. So our V is equals to E what multiplied by the D, right? And look at, we've gotten our E here. So we can even actually call this D square. This E can be written as E is equals to Q over 4 pi epsilon naught D square. Is just as if we're talking about the distance, right? So V then can be written as what? Q, right? Over 4 pi epsilon naught. Let me write that straight. Control delete. Oh. Let me write it somewhere else so we can follow. So we have that our V then equals to, because we have it as E multiplied by D, right? So E will now be what? Q over 4 pi epsilon naught D square. So we can call it D, right? Then multiplied by this D. So what will happen? This D, we cancel one D. So our V can be given as Q over what? 4 pi epsilon naught, then 1 D. And that is our potential. So do we have that now? Are we clear with that? And that's the relationship between the electric field intensity and the potential point and the potential difference. So that's the relationship between them. And the unit is what? Newton per coulomb. Unit is Newton per coulomb meter. So, and we got that. That's how we got our Q to be 4 pi epsilon naught D. I hope we are good with that. Yes. And look at this question. Two parallel plates are charged to a voltage of 40 volts. If they are separated by a distance of 10 centimeters, calculate the electric field intensity between them. As easy, so simple. We already have this, that our electric field intensity is equals to V divided by the distance, right? And since we were given the distance to be 10 centimeters, we are giving our voltage to be 40. Getting it is so easy, right? Yes, and that is it. We got it. And the answer is 400 volts per meter. Good. And this is your assignment. So simple. Apply everything you Hi dearest Efiwe, we are back again on this our excellence without stress journey, and today we are going to take another topic, which is capacitor. So today we are going to learn about capacitors and capacitance. What is a capacitor? A capacitor is a two-terminal electrical device that can store energy in the form of an electric charge. A capacitor is a two-terminal electrical device that can store energy in the form of an electrical charge. It consists of two electrical conductors. That are separated by a distance. You can see the distance. They are separated by a distance. The space between the conductors may be filled by a vacuum or with an insulating material known as a dielectric. The ability of the capacitor to store charges is known as capacitance. So a capacitor is the device that can store energy. This is a capacitor, but that ability of the capacitor to store charges is known as capacitance. So let's take that again. The ability of the capacitor to store charges is known as capacitance, but the device itself is called a capacitor. Capacitors store charge energy by holding apart pairs of positive charges. We know the positive charges, like we know the pair of opposite charges, rather. We know the opposite charges, the positive and the negative. The simplest design for a capacitor is a parallel plate, which consists of two metal plates with a gap between them. But different types of capacitors are manufactured in many forms, styles, lengths, girths, and materials. Types of capacitors. From our picture here, we can see the different types of capacitors. We have the fixed capacitor, mica capacitor, paper capacitor, film capacitor, ceramic capacitor, electrolytic capacitor, variable capacitor, and polyester. All these capacitors are different by what separates them. The film capacitor are the ones that use plastic film as the dielectric. Can you see that now? This is the film capacitors. They use what? The plastic film as the dielectric. They are available in nearly any value and voltage. up to 1500 volts. They range from 10% to 0.01% in any tolerance. Additionally, film condensers arrive in the combination of shapes and case styles. There are two types of film condensers. We have the radial type lead and the axial type lead. So this is the film capacitor. So you see the dielectric is a plastic film. So the next one is the ceramic capacitors. Ceramic capacitors are the ones, this is ceramic capacitors, are the ones that use ceramic as a dielectric material. So that is just simple ways of defining these types of capacitors. So the ceramic capacitors are the ones that use ceramic as the dielectric material. It is used in high frequency circuits such as audio to RF, that's radio frequency. In ceramic capacitors, one can develop both high capacitance and low capacitance by altering the thickness of the ceramic disc. So if we alter the thickness of this ceramic disc, we can develop both the high capacitance and low capacitance. You know what capacitance is? Is the ability of that device, which is a capacitor, to store what? Electric charges. So then we have the electrolytic capacitor. This is it, the electrolytic capacitors, and we know what's going to. So the electrolytic capacitors are the ones that use the oxide layer as the dielectric materials. It has a wide tolerance capacity. There are mainly two types of electrolytic capacitors, the tantalum and the aluminum. They are available with working voltages of up to approximately 500 volts, but the maximum capacitance values are not available at high voltage, and higher temperature units are available but are rare. And this also is another type of capacitor, the variable capacitor. This is it. Variable capacitors mostly use air as the dielectric medium. A variable capacitor is one whose capacitance can be mechanically adjusted several times. For example, this form of the capacitor is used to set the resonance frequency in LC circuits, to change the radio to match the impedance in antenna tuner device. So you can see it now. So we can alter this type of capacitor, and that is why it's called the variable capacitor. How does a capacitor work? So look at it now. For demonstration, let's consider the most basic structure of a capacitor, the parallel plates. These are the two parallel plates we have. You can see from here, plate 1 and plate 2, and there is a dielectric between it, separating the two plates. So for a demonstration, let's consider the most basic structure of a capacitor, the parallel plate capacitor. It consists of two parallel plates. Yes, this is the positive part and this is negative part. So you can notice that this is a cell, a battery are connected to it. The positive side of the cell is connected to plate 1, and the negative side is connected to plate 2. So positive charges are stored in plate 1, negative charges are stored in plate 2. So let's read. For demonstration, let's consider the most basic structure of a capacitor. The parallel plate capacitor, it consists of two parallel plates separated by a dielectric. When we connect a DC voltage across, this is a DC voltage across the capacitor, one of the plates is connected to the positive. You can see the plate, this plate is connected to the positive and the other to the negative. You can see that when the potential of the battery is applied across the capacitor, plate 1 becomes what? Positive charge, because it was connected to the positive terminal. Then plate 2 becomes negative because it was connected to the negative terminal of the battery. The current tries to flow through the capacitor. You know, ideally this current is supposed to flow, but because of this dielectric, this separation, it will just stop here and it will stop here. So the current tries to flow through the capacitor at the steady state condition from its positive plate to its negative plate, but it cannot flow. Why? Due to the separation of the plate with an insulating material. So this is how the capacitor works. This is how it is able to store charges, because ideally it collected the positive charge. This plate 1 is positively charged, plate 2 is negatively charged. Yeah, but instead of the current to continue flowing, there is a separation. This is an insulator called the dielectric. So this separation is what prevents the positive going into the negative part of the plate. So an electric field appears across the capacitor. The positive plate accumulates positive charge, yes, and the negative plate accumulates negative charges from the battery. After a point, the capacitor holds the maximum amount of charge. That is, it holds the maximum amount of charge as per its capacitance with respect to this voltage. This time span is called the charging time of the capacitor. This time span is called the charging time of the capacitor. When the battery is removed from the capacitor, the two plates hold a negative and a positive charge for a certain time. Thus, the capacitor acts as a source of what? Electric charge for a short time. This capacitor would, this plate, the plate 1, will hold the positive charge. Plate 2 will hold the what? Negative charge. So if these plates are connected to a load, this is the load, the current then flows. You can see the direction. The current then flows. Current flows to the load from plate 1 to what? To plate 2 until all the charges are dissipated from the plate. This time span is known as the discharging time of the capacitor. The time the charges are loaded into the plate is known as the charging time, and when the charges are sent to the load is known as the what? The discharging time of the capacitor. It's known as the discharging time of the capacitor. Concept of capacitors. We already explained to ourselves that capacitance is that ability of capacitor to do what? To store charges. So what are the concepts that would be meeting when we talk about capacitance? The ability of the capacitor to store charges. The conducting plates have some charges, Q1 and what? Q2. And as we saw, Q1 can be positive and Q2 what? Negative. Usually, if one plate has positive Q, usually if one plate has positive charge Q, the other has what? The negative charge. So the electric field in the region between the plates depends on the charge given to the conducting plates. We also know that potential difference V is directly proportional to the electric field. Hence, we can say Q is equals to what? CV. You remember, Q is directly proportional. The charge is directly proportional to the what? The potential difference. So Q is equals to what? CV. And C can now be equals to Q over V. I'm sure we understand how we got this. Charge is equals to C multiplied by V. This C is a constant. So the constant of proportionality is known as the capacitance of the capacitor. You know, when we say this part now, is as if I'm saying Q is directly proportional to V. Let's go to our board to try to write that. Then we introduce the constant. We introduce the constant. Q is directly proportional to V, and Q is equals to what? CV. Q is equals to CV. And if we make C the subject of formula, so C is going to be equals to what? Q what? Over V. C will be equals to Q over V. And that was how we got our C, and this is the capacitance of the capacitor. So the capacitance of a capacitor, which is a constant of proportionality, is what? Q, which is the charge divided by the what? Potential difference, because our Q is directly proportional to V. So changing the proportionality sign to equals to, we're going to introduce a constant, and that constant is C. So C is a constant of proportionality known as the capacitance. That's the ability of this capacitor to store charges. Capacitance is a ratio of the change in the electric charge of a system to the corresponding change in its potential. So that's the ratio. You can see it now. Capacitance is the what? Is the ratio of the change in the electric charge. This is the charge of the system to the corresponding what? Change in its what? Electric potential. The capacitance of any capacitor can be either fixed or variable depending on its usage. From the equation, it may seem that C depends on the charge and voltage. Actually, it depends on the shape and size of the capacitor, and also on the insulator used between the conducting plates. You know, we talked about different insulators, the film, the ceramic, and so many other types of capacitors. So energy stored in a capacitor. Once the opposite charges have been placed on either side of the electric plate capacitor, the charges can be used to work by allowing them to move towards each other through a circuit. The equation gives the total energy that can be extracted from a fully charged capacitor. So the energy in a capacitor is given as 1/2 CV squared. That's 1/2 CV squared, and that is how to get the energy stored in a capacitor. Capacitor functions a lot like rechargeable batteries. The main difference between a capacitor and a battery lies in the technique they employ to store energy. Unlike batteries, the capacitor's ability to store energy doesn't come from chemical reactions, but from the physical design that allows it to hold negative and positive charges apart, and that's by putting what? The dielectric between the two plates, and that is the ability that the capacitor has. Standard unit of capacitance. The basic unit of capacitance is the farad. Yes, the capacitance is measured in farad, but farad is large unit for practical tasks. Hence, capacitance is usually measured in sub-unit of farad, such as a microfarad. Most times, this is the unit we use for the capacitance, micro or the picofarad. So 1 microfarad, 1 millifarad is times 10 raised to power minus 3, microfarad is times 10 raised to power minus 6, nanofarad is minus 9, and the picofarad is what? Minus 10 farads. And this is the capacitance of a parallel plate. You can see that this one is one that is going to hold the what? Positive charge. This one is the negative charge, and this is the distance, the dielectric, the separation. So this is the parallel plate capacitor. So now we are going to capacitance of a parallel plate capacitor. The parallel plate capacitor, as shown in the figure, has two identical conducting plates. I'm sure we can remember that two plates, plate 1 and plate 2, each having a surface area A and separated by a distance D. Yes, there was a separation, and that separation is where the dielectric material is kept. When voltage V is applied to the plate, it stores charge Q. The force between charges increases with charge values and decreases with the distance between them. So also, the bigger the area of the plates, the more charge they can store. Let's not forget that is the capacitance of a capacitor is directly proportional to the area. A bigger area means more capacitance, like more ability of the capacitor to do what? To store charges. So capacitance is directly proportional to the area. Similarly, the closer the plates are, the greater the attraction of the opposite charges on them. So therefore, C is greater for a smaller d. So what is this saying? It's telling us that the capacitance of a capacitor is inversely proportional to the distance. So the smaller, look at this part now, the smaller the distance between these plates, the more the capacitance ability, the more the ability of the capacitor to store charges. That is what it's trying to say. And the area, it is directly proportional to the area, directly proportional. The bigger the area of the plates, the bigger the area of these plates, the bigger the area of the dielectric of the plates, the greater the capacitance of the capacitor. So let's try to get another equation for the capacitance of a capacitor. You know, we've already accepted that the capacitance of a capacitor is the charge divided by the potential difference. That's the ratio of the charge and the potential difference. So remember that we have that E is equals to what? Electric potential difference divided by the distance between the two plates. E is equals to electric potential difference divided by the distance between the two plates. Then we have E is equals to V over D, and you know, making V the subject of formula, we have our ED. We have our ED. So V also, from our previous classes, we established that V is equals to sigma multiplied by the distance divided by epsilon naught. We've established this, sigma multiplied by D divided by epsilon naught. So also, we know that our C is equals to Q over V. Don't worry, we'll go to our board to quickly explain. We'll go to our board to explain. So C is equals to Q over V. What are we then going to do? We are going to put this value of V into this equation, and putting that, we are going to get this, that our C then is Q multiplied by the epsilon naught divided by sigma multiplied by D multiplied by D. So let's go to our board quickly to see what we are talking about. So look at it now. From the board, we already have that our V is equals to sigma. Let's write that very straight. Control Z. We have that our V is equals to sigma D divided by epsilon naught, right? And our C is equals to Q divided by V. Our C is equals to Q over V. So now, it's just as if I'm saying C is equals to Q divided by Divided by V. Then what will I now do? Then Q divided by putting that value of V we have, which was sigma multiplied by D divided by epsilon naught. So putting it in now, what are we going to do? We're going to have to change this division sign to multiplication. So it's going to be Q times epsilon naught divided by sigma D. So our C then can now be Q epsilon naught then sigma, and what? And D. So we've established. But this Q over sigma is a value. So C can also be what? C is equals to A, because Q over sigma is equals to area. Charge over the sigma is equals to what? Is equals to area. So it's A divided by what? That's going to be A epsilon naught over what? Over D. And this is another formula for our C, our capacitance of the capacitor. So let's go to our board, our slide, to check it again. So you can see now that we have that our capacitance of capacitor is now equal to this. This is epsilon naught is the permittivity of free space, C is the capacitance of the capacitor, A is the area, and D is the distance. So we have gotten another formula for the capacitance of a parallel plate capacitor. So this is an example. We want to solve this question. Calculate the capacitance of an empty parallel plate capacitor with metal plates with an area of what? 1 meter square separated by what? 1 millimeter. You know, we have to convert this to meter, and that is 1 times 10 power minus 3. So having this formula now, can we get our answer? Yes. Epsilon naught is a constant and the value is 8.85 times 10 raised power minus 12. So putting in all the parameters we have our area to be 1 meter square, we have our distance to be what? 1 times 10 raised power minus 3 meter. And putting that, so we have this to be this, we have our area to be 1, we have our distance to be 1 times 10 power minus 3. Putting this and multiplying it, we have this. And you remember that when we're talking about the unit for capacitance, we told you that 10 times 10 minus 9 is nanofarad. So this is 8.85 times 10 power minus 9 farad, and this can be represented as nanofarad. So you just have 8.85 nanofarad. So factors affecting capacitance, the factor affecting the ability of a capacitor to store charges, the factors affecting them. Number 1 is a dielectric medium. The effect of dielectric on capacitance is that the greater the permittivity of the dielectric, the greater the capacitance. Likewise, lesser permittivity of the dielectric, the lesser is capacitance. Some materials offer less opposition to the fluid flux for a given amount of field force. Materials with greater permittivity allow more field flux, hence greater charge is collected. So the dielectric medium has a great effect on determining the amount of charge that the capacitor will be able to store. The second is the plate placing. You know, we've talked about this, we already explained this. I told you that the first one is telling us that the type of dielectric material we use affects it. The type of dielectric material tells us the amount of charge the capacitor can store. The ability of the capacitor depends on the dielectric material. Another one is the spacing. The spacing, you know, I said that C, capacitance of the capacitor, is inversely proportional to the what? To the distance, to the plates, to the separation between the two plates. It is inversely proportional. So big separation, small capacitance. Small separation, big capacitance. The last is what? The area of the plate. The effect of the area of the plate is that the capacitance is directly proportional to the area. The capacitance is directly proportional to the area. The larger the plate area, the more capacitance value. And this is it. Directly proportional and inversely what? Proportional. I know that we know how to do this, so let's go to the next slide. So now we have the parallel arrangement of capacitors. Just the same way we talked about the arrangement of resistors, we have also the arrangement of capacitors, just as we did for resistors. But the only difference is that the way parallel capacitor works is the way series is the way series resistors work, and vice versa. So the total, this one now is called this capacitors are connected in parallel. They are connected in parallel. You can see the parallel, this thing. They are connected in parallel. The total capacitance of the capacitors connected in parallel is just their addition. You know, recall that for resistors, this was the series, what's it called? This was the series connection. When we wanted to calculate the total resistance, that's when we use addition. That's when we use addition. So, but for the capacitor, it is the parallel arrangement that we add together. So you're just going to well, C1 plus C2 plus Cn and so on and so forth. Also, the series arrangement is like the parallel arrangement in the resistors. So the total capacitance of the capacitors connected in series are 1 over C1 plus 1 over C2, as we can see from this place. So energy stored in a capacitor. So we have that E is equals to 1 over 2 QV. 1 over 2 QV. So let's go to our board to derive it up to this point. 1 over 2 QV. 1 over 2 QV. So we have that our E is equals to 1 over 2 QV. And don't forget, this Q has a value. Recall that your C is equals to what? Q over what? Over V. And if you cross multiply, you can have that your what? Your Q will be equal to what? CV. So putting this, so we have that our E is equals to 1 over 2 what? Q what? V. So putting this in this equation, so E will be equals to what? 1 over 2. What is our Q? That's CV, right? Multiplied by the V that was there before, multiplied by this V. So E can also be what? 1 over 2 CV what? Square. CV square. Also, our V can also be what? V can be Q over C, right? So let's put that into this equation. We have that our E will be equal to what? 1 over 2 C, right? Then V, which is now square, will be what? Q over Q square, right? Over what? Over C square. So if 1C cancels 1C, our E will be equal to what? 1 over 2. We still have our Q square, right? Over what? Over C. And these are the formula for the energy stored in a capacitor. Energy stored in a capacitor. So that's how to get all the formulas. So example, two capacitors of capacitance 5 microfarad and 3 microfarad are connected in series, and the resulting combination is connected across 600 volts. 1. What is the equivalent capacitors of the combination? And 2. The total charge on the combination. You don't forget that we've already agreed that when capacitors are connected in series, to solve the equivalent capacitance, it's just the inverse addition, that is 1 over C1 plus what? 1 over C2. 1 over C1 plus 1 over C2, and we have 3 and we have 5. So let's go to our board to quickly do that. Let's delete the board. Okay, so we already have it that 1 over C total is equals to 1 over C1 plus what? 1 over C2. So 1 over C total is equals to 1 over 5 plus 1 over 3. So what are we going to have? We're going to have 15. So that will be 5, right? So 3 plus 5. So 1 over C total is equals to 8 over 15. But we don't stop here, because we're not looking for 1 over C total. We're looking for our CT, and our CT will now be equal to what? 15 over what? Over 8. So we have gotten our C total. So what else were we asked to look for? What else were we asked to look for? We were asked to look for what? The total charge on the combination. The total charge on the combination. Don't forget, Q is equals to CV. Don't forget, Q is equals to CV. And so we can do our normal multiplication. We've gotten this. When we did our division with the microfarad, we got this times 10. Oh, sorry, this is times 10 power minus 6 here. So putting that into this equation, we have our Q. Our Q to be equal to what? CV. So whatever we got, which was what? 15 over 8 microfarad multiplied by our V, which is what? 600, will give us our what? Our charge Q. And that was what we did. That was what we did here when we said what? Q is equals to CV. Our C was what we got here, and it was 1.87 times 10 raised to power minus 6 farad multiplied by the V, which was 600, and we got this as the charge, which is in column. Let's go to the next question. A capacitor of capacitance 5 microfarad is subjected to a potential difference of what 1000 volts across its terminal. Calculate the energy stored in the capacitor. So we have to check the formula we are given. We were given the capacitor of a capacitance, we were given the volts. So what is the normal formula to use to find the energy, like all the work done? So the W, which is this, is 1/2 CV square. I'm sure we derived all this formula in the previous slide. 1/2 C. And what was our C? 5 times 10 raised to power minus 6, because this is microfarad. Then multiplied by the volt, which is what? 1000 volt across its terminal. And we're able to get this, and we're able to get this. We had 1000, but 1000 square was what we wanted to use, because the V is squared. That's why we have it as 10 raised to power 6 here. And when we do our normal calculations, we are going to get what? 2.5 joules. We're going to get 2.5 joules. What are the uses of a capacitor? The capacitor have both electrical and electronic applications. They are used for several things, such as filters, energy storage system, engine starters, signal processing devices, etc. Capacitors are used for storing energy, which can be used by the device for temporary power outages whenever they need additional power. Capacitors are used for blocking DC current after getting fully charged, and yet allow the AC current to pass through the circuit of a circuit. Capacitors are used as sensor for several things, like measuring humidity, fuel levels, mechanical strain, etc. Capacitors can also be used in a time-dependent circuit. This could be connected to any LED or loudspeaker system, and it's likely that any flashing light or regular beeping uses a timing capacitor. And this is your assignment. So you can see this now. These two, you check, are they connected in series? Yes, these ones are connected in parallel. Then you are going to resolve it, and this one which is connected in series too, you have to resolve this first and change it to series before you can come and solve this. You know, in parallel you just add, and in series what do? You find the inverse 1/, of this. So the same thing goes to this place. You would find the equivalent capacitance and solve it, and also for